in the exercise book, I am on page 22. I'm falling out of my chair again. Number 15. 2 gallons of paint cover 800 square feet, and you want to paint 1,800 square feet. So let's go ahead and set up the ratio of gallons to square feet. 2 gallons cover 800 square feet, and we want to paint 1,800 square feet. How many gallons of paint do you need? And assume that you can purchase partial gallons as needed. You don't have to buy a whole gallon if you just need a fraction of a gallon. So 2 times 1,800 is going to be 3,600. And then divide that by 800. And that will be 4.5. So you need 4.5 gallons of paint. That is answer C. Number 16. In your household, 4 out of 10, that's a ratio, 4 out of 10 pieces of mail are not read. So of 10 pieces, 4 are not read. If you receive 2,500 pieces of mail over the course of a year, that's pieces. Those have to line up together there. How many pieces of this mail are not read? So the peanut will be 4 times 2,500. And that is 10,000. Divide that by 10, and you will get 1,000 pieces. And I'd say at my house, that is definitely true. That of all the mail coming in, that's a pretty good ratio of not read. So I like answer D on that one. Number 17. A 1.2 ounce bar of almond candy contains 230 calories. So we are comparing ounces and calories. And 1.2 ounces contains 230 calories. A 4-ounce bar of almond candy contains about how many more? So at some point I have to subtract. How many more calories than the 1.2 ounce bar? So let's bring this up to 4 ounces and see how many calories we're going to get. So 230 times 4 is 920. Divided by 1.2. And that is scary looking. Oh, about how many more? So we're going to have to round here. So I'm going to make this correct mathematically. And let me zoom in so you can see. It is approximately, that's that squiggly equals, 767 calories in 4 ounces. And then here comes the subtraction. Notice answer D there is 767. We're not finished. We have to find the difference between those two. So 767 calories minus 230 calories. You want those units to be the same. You're not subtracting the ounces. I'm thinking a difference of 537. So I like answer A for that one. Number 18. How many seconds are there in a day if there are 18,000 seconds in 5 hours and 24 hours in a day? So we are comparing seconds to hours, essentially. You could compare it to a day if you wanted to, but you would need to convert. So I'm still going to have to convert, but I think this is an easier conversion. There are 18,000 seconds in 5 hours. And then we want to use 1 day here. That's 24 hours. You just want to be sure that everything on this row is in hours. And everything on this row is in seconds. So I will have 18,000 times 24. That is a lot, but we're talking about something that is a lot. You get 432 with 3 zeros, and you divide that by 5, is 86,400. So I like answer D for that one. Let me go ahead and finish what that is the number of seconds in 1 day. Number 19. A bread recipe calls for 5 parts of whole wheat flour to 2 parts chickpea flour. So whole to chickpea. I don't know what chickpea flour is, but that whole recipe sounds kind of nasty. I don't think I would like that. Okay, 5 to 2. You have 1 1/3 cups of chickpea flour and 4 cups of whole wheat flour on hand. So let me go ahead and write these down. On hand, you have 1 1/3 cups of chickpea and 4 cups of whole wheat. If you bake the largest loaf possible using this flour, how many cups of whole wheat flour will be left over? Now, this is not exactly like the lemonade problem. It's the same kind of concept, but it's not exactly the same kind of solution. So let me think through how best to explain this. What we're really looking for is how much flour is left over. So we will have to do some subtraction at some point in this problem. Okay, let me do it this way. Whoa. Would you agree with me that the wheat flour is not a problem? The wheat flour, I have 4 cups. Actually, it is a problem because it's 5 parts. Let's approach it another way. Would you agree with me that the least amount of ingredients that I have will be in the chickpea category? I have less chickpea flour than whole wheat. So this is where I'm limited. I can only use what I have. So I can't use more than 1 1/3 cups of chickpea flour. I don't have any more than that. So let's set up a proportion using that number because that's where I'm limited. So I'm going to set it up as the recipe of whole wheat over chickpea. That's just how the recipe was given to us. And the standard is 5-2. That's what the ideal amounts would be. But we don't have 2 cups of chickpea flour. We only have 1 1/3. And that's what I'm going to put right in here. So 1 1/3 cups of chickpea flour. So here's the peanut. We've got 5 times 1 1/3. And your calculator will do that no problem. So 5 times 1 and 1 and 3 equals 6 2/3 cups of whole wheat that are needed. But that was not the question. The question was, if I put the 1 1/3 cups of chickpea flour in, how many cups of whole wheat flour would be left over? And I haven't finished my proportion. I hope you caught that. It is almost 11 o'clock and I have not had dinner, so that's my excuse tonight. I failed to do this. That was not intentional. I just made a careless mistake. But I realized that I had made a careless mistake when I went to subtract these two. So if you dump all the chickpea flour you have into a bowl, you will need 3 1/3 cups of whole wheat to go with it. We are reducing this recipe to match the ingredients that we have. So you have 4 cups of whole wheat. You only need 3 1/3 cups in this reduced recipe. So 4 minus 3 and 1 and 3 is 2/3. So you will have used all the chickpea flour, but you'll have 2/3 of a cup whole wheat left over. I actually did something very similar to this the other day. I bought an Amish cookbook and the recipes are wonderful. But I made a loaf of bread very similar to this 5-2 thing. It didn't have chickpea flour in it, but that thing kept getting bigger and bigger and bigger. So when I made it the second time, I reduced the recipe because we just can't eat something that big. But I use this all the time in the kitchen. This kind of problem is very, very handy to know. Okay, number 20. Gregory has decided to run a marathon. He has been running 5K races to prepare for the marathon. He knows that a marathon is 26.2 miles and that 5 kilometers is approximately 3.1 miles. How many kilometers would he run if he ran a marathon? So in this one, the comparison is kilometers to miles. So we're comparing units from the metric system to units from the standard system. And he knows that a full marathon, is 26.2 miles. He also knows that 5 kilometers is approximately 3.1 miles. So how many kilometers are in a marathon? That's the answer that we're trying to find there. So we'll multiply 26.2 times 5. And that is 131. And divide that by 3.1. And we will get 42.25.26. Again, that's an approximation, so I need to make a squiggly equals. It's been rounded. And they went ahead and rounded it yet again to 42.3. And that is answer C. There are 42.3 kilometers in a marathon. More power to Gregory. I can't imagine running that many miles at one time, or at all in a lifetime. Okay, number 21. Students I have had before in class literally panic at this kind of problem. We've seen these in science. Don't panic. It's okay. Gravity is the force that determines our weight. The gravity on Earth is approximately 9.8. I guess that's meters over something squared. I'm not sure what that stands for. Whereas the gravity on the moon is approximately 1.6 over ms squared. Now that's going to drive me crazy. Where's my cell phone? Let's figure out what that's talking about. And I should know that anyway. M divided by s squared. That's the measurement of gravity. But what is that talking about? Well, I know what. 1 meter divided by a second squared. Okay. For us, that's irrelevant. We're going to work this without even knowing that. If someone weighs 180 pounds on the Earth, what is the weight on the moon? So here's what we're trying to find. Now, does this help? Sure does. Because it doesn't matter what this is. It's the same top and bottom. So as long as it's the same unit, we're just going to let it go away. Pounds is the same unit, so we're just going to let it go away. And now what do we have? Our good friend, the peanut. This time the peanut goes this way. So 180 times 1.6 is 288. Divided by 9.8 is approximately 29.39 if you round it. And they've gone ahead and rounded it yet again to 29.4 pounds. Now, because this, let me get that. This is C, the answer. Because this is such a common question on science tests, I want to go ahead and tell you a little bit more here. I want you to imagine that this, you guys are going to laugh, this is Neil Armstrong, who walked on the moon. On Earth, Neil weighs, I'm just making this up, I have no idea how many pounds he weighed, but I'm just going to use 180 pounds. We'll use the example that they used. So when Neil goes to outer space, does he shrink? Does he lose weight? Or is he exactly the same person on the moon? I don't know how long that trip took, but it couldn't have taken long enough for him to lose weight and for him to be any different. He's the same man, regardless of where he is. It's like if I weigh whatever I weigh at home and I go to Walmart 5 hours later, I still weigh the same. I'm the same person, regardless of where I am. But on the moon, Neil would weigh about 30 pounds. So how can we explain that? His mass is the same. His mass is exactly the same. He has the same mass that he has here in this picture. But his weight is different. And that is because weight is a measure of the pull of gravity. And gravity is a pulling force, not a pushing force. There's not a giant hand in outer space pushing us down on the earth. There is a force at the center of the earth and in between the sun and the earth that is pulling us to the ground. So weight changes, but mass does not. And that is an incredibly important thing for science. And another thing that you will want to know, if you want your moon weight, you take your earth weight, and this is weight, not mass, because mass won't change, not in this situation. You take your earth weight divided by the number 6, and that will give you your moon weight. So let's say that Neil only weighed 120 pounds on Earth. So 120 divided by 6 means that on the moon, he would only weigh 20 pounds. And then when he came back to Earth, you would do 20 times 6. He would weigh 120 again. That has nothing to do with math here at all, but it is such an important concept for science. It's worth taking the time to study. Okay, let's check these answers for page 21. And I have number 11 is A. Number 12 is C. 13C. 14A. 15C. 16D. 17A. 18D. 19B. I didn't get that one, did I? I didn't mark it. I'll have to go back and check that one. And 20 is C. 21 is C. So 19 should be answer B. And that was page 22. Yes, that is correct. I just forgot to write it down as usual. So 19 is B, 2/3. That's right here. So we are okay on that one. And I'm going to stop this video. We will come back for page 23.